it's a pleasure on behalf of the organisers to welcome Chris Burdzy, who's here as the distinguished Rothschild Fellow visiting the programme on stochastic systems for anomalous diffusion here at the Isaac Newton Institute. So Chris was educated in Poland and California and has been at the University of Washington since 1988. So Chris has written many papers, over 150 papers, and on a variety of topics, and 6 books, including topics from multidimensional Brownian motion and foundations of probability in its philosophy. He was awarded the Waller-Davidson Prize, among several other honours. He's very well known for his editorial work, service across the community for many years, including one of the founding editors of the electronic journals in probability. And last thing I should say, very recently was president of the Institute of Mathematical Statistics. So it's a great pleasure to welcome Chris today, and he's going to tell us a bit about Archimedes Principle. Please.
Well, thank you very much. It's a great honor to be a Rothschild Fellow. It's a great pleasure to give this public lecture. Let me take this occasion to thank the organizers of the program for inviting me. And I also thank all of you for coming to this lecture under these circumstances, tropical weather. Okay. So Archimedes' principle says that the upward buoyant force that is exerted on a body submerged in a fluid is equal to the weight of the displaced fluid. There are 2 types of fluids, liquids and gases, and Archimedes' principle works different in liquids and gases. Titanic had no choice but to either float on the surface or to sink to the very bottom of the ocean. And the reason is that pressure is a linear function of depth. And if you think how it affects what you can do, well, it's either you're at the surface or at the bottom. And all objects, natural objects like fish, whales, or man-made objects like submarines that are in between, they have to use active control. But it's different with gases. A helium balloon, if you release it, it will go up, 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 and then it will stop. It will float at a certain height. And today I will be talking about Archimedes' principle in gases. So I will consider a microscopic object floating in a gas. So first I will argue that Archimedes' principle is trivial. And there's no mathematical literature on Archimedes' principle because there's no point. It's a trivial statement. I'm not suggesting that divergence theorem is trivial. What I'm saying is that if you know divergence theorem, then Archimedes' principle is a simple corollary. But this assumes that you already have the concept of pressure and you have some kind of formula for pressure. And then you can effectively prove Archimedes' principle. Okay, and now let me argue that Archimedes' principle is non-trivial. Well, it depends how you want to prove Archimedes' principle, and what I try to do with Zhenchin Chen and Shumik Pal is I try to derive it from, let's call it, lower level physical theory. Now, personally, I like my paper very much, but there were some problems with that model. I mean, not mathematical, but sort of philosophical problems. In that paper, we assume that the number of particles is fixed, but it was a limiting result, right? That an asymptotic theorem we assume that gravitational acceleration went to infinity. And but in reality, both numbers are fixed. The number of particles is fixed, or molecules of gas is fixed, and a gravitational constant is fixed. But we sort of think that gravitational constant is fixed and the number of particles goes to infinity because there are so many of them that it's very natural for us to think that it's the number of particles that goes to infinity. And there was another problem. Well, problem. It's not a problem. It's just that we started from, not from the fundamental physics, but one level up. You know, molecules of gas move like Brownian particles on a certain scale, but this is not the most fundamental theory of matter. I mean, Newtonian mechanics, or if you wish, quantum mechanics is below that. So today I will talk about my second project on Archimedes Principle with Jacek Małecki. And, well, so the new project, in this new project, the gravitational acceleration is fixed, the number of particles goes to infinity, and we do not start with Brownian motion. We do not assume that molecules move as Brownian motion. We assume that they move according to Newton's mechanics. And, well, if you wonder why anybody would bother to do that, but I would say this, in mathematical physics, it is quite common to try to derive macroscopic phenomena or to prove macroscopic results from assumptions about microscopic laws of nature. And there are all kinds of models of this type. Okay, so now I will be a little bit more specific. I will talk about ideal gas. Well, ideal gas is ideal gas, and it's not a realistic gas, but, well, I did not invent ideal gas, so I can blame somebody else for inventing this. In ideal gas, molecules are point-like. So these are points. But they have mass. So they move in gravitational field, you know, along parabolas. And they bounce from the walls of a container. Our container will have a nice base. And semi-infinite walls. There's no point of putting like a top on that container because the energy is finite, so that if you have a semi-infinite walls, I mean, the molecules will never escape. There isn't enough energy to send them to infinity. And our macroscopic objects will be a ball. Now here I represented molecules of gas as little spheres, but just to make the picture a little nicer, but actually there are points. So ideal gas with points, point-like molecules. So here it is, Archimedes Principle. Well, we present it as a limit theorem. The number of gas molecules per unit volume is large, so actually if it goes to infinity, right, then the height of the macroscopic ball in ideal gas is close with high probability to the point prescribed by Archimedes' principle. So the number of particles of molecules goes to infinity, and you may think, okay, so it means that there will be more and more gas. So no, that the mass of gas is fixed. The number of particles goes to infinity, but then the mass per particle goes down, so that we always have the same mass, the total mass of gas. So this is the kind of theorem that we put. So this is an informal statement, but actually it's true and accurate, but I want to explain some things that are not explained explicitly in this statement. So first of all, I will start with a point prescribed, I mean the height prescribed by Archimedes' principle. I want to explain what I mean by that. And also I say high probability. Like what probability? Okay, so I will explain both parts of the statement. But first I want to say a few words about barometric formula, because I will use it in one of the formulas, so I should tell you or remind you what it means. The barometric formula is the formula for the pressure above the ground, and it says that it's exponential as a function of height. And actually, it's not hard to derive if you make two assumptions. So first of all, pressure is force, and weight is force. Weight is a form of force, and pressure is force per unit area. So pressure is proportional to the weight of gas that is above the given height. And then if we use the gas law, PV over T equal to C, then a simple calculation shows that pressure has to be exponential. Although we will use, I would say, related formula, because we will not use this formula for pressure. We will use this formula for the density of gas, right? The mass density, which is not the same as pressure, but I guess you can believe that the same formula applies.
T is temperature.
Again?
T is temperature.
T.
Yeah.
Temperature, yes.
So
Pressure, volume, and temperature.
it sort of exists and it's the same around the volume.
Okay?
So the temperature exists and it is the same around the volume.
Yes. Yes. So that's the assumption, and this actually can be. So that there was a remark here about the constant temperature. So the constant temperature actually, this follows from what I will show later, a formula called microcanonical ensemble formula. And if you believe in that formula, then the temperature is constant. Okay. So now a little bit of mathematics. So formula 1 is actually Archimedes Principle. It looks complicated, so let me try to say a few words so that you can understand what's going on here. So first of all, the way normally my Archimedes Principle is formulated, it is in terms of weight. The weight of the object is the same as the weight of the displaced gas. But since this is weight equal to weight, and in my model the gravitational constant is the same, we can simply state as mass equal to mass. So there is no gravitational constant. For weight, you would just multiply both sides by g. Okay. So on the left-hand side, there's the mass of the ball. You can think about this as a balloon. The right-hand side is complicated, but let's just look at the upper integral. I will not go into details. The upper integral simply means this is the amount of gas that was displaced, right? Because the mass of the floating object has to be equal to the mass of the displaced gas. So the upper integral is the integral over that ball, and it says, well, this gas is missing, right? So this is the displaced gas. But then, what is this m and this integral? You see, this is the change of units. The upper integral expresses the amount of gas in some abstract units. Who knows, maybe they are like chemical units, moles. And I have to convert the units so that I have the same units as on the left-hand side. Say the units on the left-hand side are kilograms. So how do I convert the units? Well, I convert the units by saying, well, if I have m kilograms of gas, then I divide by the amount of gas, whatever that amount is, like chemical moles or whatever, quote unquote, some kind of units amount. And here I integrate not over the ball, but outside the ball, because the gas that is there in the container is outside the ball. So that little m over that integral is simply that, you should think about this as unit conversion, from some abstract units to actually kilograms. Now, so we are interested in the height of the balloon, or the height at which it is going to float. and this is little y. But I claim that actually there are two unknowns in this formula. Okay, so let's try to think in physical terms, or in terms of an experiment. If I do an experiment, I choose the vessel, D. I choose the balloon, or the ball. So this is the ball, the mass of the ball, or the balloon, this is the radius. That's my choice. So it's given, right? And then I pump some gas into the container. But then I claim that the height and lambda are unknown. So you have to believe me that lambda is inverse temperature. We actually prove it, and this is, I guess, in physics it is just probably taken for granted. It's just obvious, I don't know, but we actually prove that for our model. So think about lambda as temperature, except that it's inverse temperature. So I claim that y and lambda are unknown. Why? Because the experiment that I have in mind is that, I pump some gas into that container, I throw the ball in, and then after some time, presumably the system will reach equilibrium. And the balloon will float at a certain level. But you see there are several kinds of energy inside. Well, kinds. There are only two kinds. There's potential and kinetic. And the balloon can have potential and kinetic energy, and gas can have both potential and kinetic energy, and somehow the energy will distribute itself, which means that the system will decide what temperature it will have, right? So what portion of energy will go into kinetic energy. Now, I could, in principle, choose the temperature by heating or cooling the system, but that would be a different model, because in my model, it's an isolated system. I cannot touch it. If I heat or cool it, then there would have to be some other element in which I can, add energy or take away energy from the system. So in my system, I do not control lambda. Okay, so what can we do about that? Well, we get some help from a pretty standard concept in physics. Energy is conserved and energy is additive. So now I have another equation. And in this equation is the total energy, right? The energy that went into the system, the potential and kinetic. And let's go from the right. mgy, this is the potential theory, the potential energy of the balloon. This complicated, this is similar to this. This is, you have to believe me, this is the potential theory energy of gas. Basically integrate, that exponential distribution, and what you get is the potential energy of gas. Right? Think about every layer has some potential energy. And finally, this is the heat energy, because now lambda is in the denominator, right? So 1 over lambda is temperature. You multiply it by the mass of gas. There are some normalizing constants, and what you get is the heat energy. And in this way, we get the second equation. Please note that the kinetic energy of the balloon is missing because in this model, we get equilibrium and the balloon is not moving. So no kinetic energy. Please note that all these equations and everything that I said, all my remarks related to this slide do not mention molecules. There are no molecules here. What I'm using, yeah?
I'm allowed to ask more questions. I'm still trying to understand what the numerator in Formula 1 means.
The numerator, this is the amount of gas that is displaced, meaning that I integrate over the ball, and I integrate the density of gas, and that's missing. So this is the amount of gas that is missing.
This is the integral in radius. What's the integral in x?
all bad notation. This is just multidimensional integral, two-dimensional, three-dimensional, depending on your space. But this is simply the integral over the ball. So, sorry about this. This is bad notation. X was x. X in my y is height. X are all horizontal coordinates.
And this is exponential because of the low pressure, which you showed in the
Yeah, the barometric formula.
Yeah, okay. But somehow the formula is not in that direction. Somehow it's in any direction.
Well, so here R is supposed to be the vertical coordinate.
Yes.
Sorry about this, but R is the vertical coordinate, and as for all other are just uniform. Okay, so please note that there are no molecules here. What I did here is I took known macroscopic laws of physics or laws of nature. What I did is I wrote two equations based on simply assuming that they are true. Right? So this gives me a prediction. If I solve these equations for y and lambda, this gives me a prediction that, like experimental prediction. And we proved that actually these equations have a unique solution. And let me point out that this is not obvious because these are, like if you have two equations and two unknowns, these are linear equations that most of the time you get a unique solution. For nonlinear equations, there's nothing even remotely similar. So I would say somehow nature is nice enough to give us a unique solution. And we were lucky that we found a proof of that, because at least we could not find an easy proof. So this is actually quite a, but our proof takes some effort. And now I want to make a claim. I claim that this is not only a mathematical theorem. This is we discovered a new law of nature. In the following sense, I claim that this result cannot be derived from known laws of nature. At least I don't know how to do it. And let me explain what I mean by that. Suppose that you have this container that the boat is floating at a certain level and then just randomly changes its height. Right? Just randomly. And stops there. So what's going to happen is that the potential energy of the ball will decrease, right? So something has to happen with this energy, and that energy has to go to gas. So the energy of gas will go up, and it will increase both potential and kinetic energy of gas. Well, at least common sense suggests that both will increase, not just one of them. But what this means is that the gas, if its potential and kinetic energy increases, is the gas will be spread more, right? So that right, the hot gas will spread, or if you put more energy into gas, it will go up. But what it means that at the level of that ball, of that level, you will have less gas. So it is theoretically possible that the amount of gas that you displace at the lower level somehow perfectly balances. And everything somehow perfectly balances, and you get two solutions. And my claim is this. A hand-waving argument will not eliminate multiple solutions. So this is why I say that this is a new law of nature, because it does not follow from known laws of nature by some sort of simple and intuitive argument. You have to actually do calculations. Okay, but there's no probability here. So let's talk about probability, because I said that the balloon will be at a certain height, rather close to a certain height, with high probability. So what's this probability? Well, I assume that the system is in the stationary region. Now, the system that I consider is deterministic. So when the system evolves, there's no randomness, there's no probability. The only probability there is that I assume that all the objects, so the small objects, the molecules, and the big object, are distributed according to the invariant measure. And this gives me probability, because it's a probability measure. So let me say a few words about this then. So the formula is a special case of what I guess in mathematics would be called the Liouville measure, and in mathematical physics, microcanonical ensemble formula. So these are, I guess, well-known concepts, ideas. So Liouville measure is a measure that for a dynamical system is sort of invariant. Somehow the dynamical system makes that measure invariant, somehow carries that measure. We could not find this formula anywhere. We contacted some people in math physics community, in PD community, and so on. So I don't know. As I say, Liouville measure and microcanonical ensemble formula are concepts that are well known, but this formula we just could not find. And by the way, you see different names because this was a different, like a parallel project on Fermi acceleration, whatever that is, and it's just the derivation fit well into that paper. Now let me try to explain because this is a complicated formula, but I think that I will be able to at least give you an idea what's going on here. So there are two factors, and in this formula, the potential energy and the kinetic energy are separate. So the second factor represents the kinetic energy, and the way to think about this is this. Suppose that we know the potential energy. We fix potential energy, therefore all the remaining energy has to be kinetic. And that sigma, this stands for equidistribution of energy. Let's suppose for a moment that all masses are the same, so we don't have to deal with masses. Now, write all vectors, all velocity vectors, as a single vector. So if we are in a three-dimensional space, if you have 1,000 objects, you will have a single 3,000-dimensional vector. Since the energy is fixed, it means that the sum of squares is fixed. But if the sum of squares is fixed, we are on a sphere. But if we are on a sphere, the formula says that it's the uniform distribution.
So sigma is spherical.
Sigma here stands for the uniform distribution of the sphere. So once again, once you assign some portion of energy to potential theory, potential energy, everything else is uniformly distributed on the sphere.
Are they one-dimensional or multi-dimensional?
In this, they are all one-dimensional, because it doesn't matter how you present it. You could go with say, three-dimensional vectors, but in the end, you will get IID normal. For those of you who are not familiar with this, if you have the uniform distribution on high-dimensional sphere, then all coordinates are almost IID normal. So basically, all components of all velocities are independent normal, approximately.
So Chris, is there any dependence on the VI's in the integrand?
Wait a minute. What integrand? You mean like on previous page, or?
Well, the E, the thing with the power. What's the dependence on VI in?
On the left?
Yeah.
Yeah, so on the left there isn't any. So this is a density, so you should think about this as a density. So yi's, okay, mi's, g, e are constants, and the masses are constants. So the variables here are yi and vi. So this is the density, the joint density for the positions and velocities. And what I'm saying is that if you fix the positions, then the velocities are uniformly distributed on the appropriate sphere.
So do you assume that you have a ball or just cylinder where the
Over here?
Yes.
Okay, it's a very good question. In this formula, we have essentially point-like objects, because in this formula, as it is, there are no hard spheres. They can go through each one like ghosts. So think about, you know, point-like, or this could be balls if you wish. But this describes the invariant measure for the centers of these objects. And please note that in part 1, there are no collisions, which means that they simply don't see each other. They go through each other like ghosts.
You see the ball.
Nothing. I mean, they just go through.
Just go through the ball. Because when
Yeah.
you consider...
No matter what objects, you can have big balls, small balls, points.
I mean, your big ball that is flowed.
Yeah. So in part 1, there are no interactions. Molecules go through the ball. And then in part 2, what I'm saying is that the same formula applies if objects collide.
Okay, so maybe I can restate this. So the pair of x and y directly belongs to the physical shape of the container.
The formula applies to the whole space. There's no container, no walls. I mean, the first version of the formula is a sigma finite measure, infinite measure. It's on the whole space, and it's invariant for the motion of objects under gravitation.
And if you put this in a container, the formula will...
And if I put it in a container, then we go to part 2. Because in a container, there will be collisions, because there will be collisions with walls, and there will be collisions with the object, between the objects, so spheres. And collisions with the walls and collisions between the objects. And then the claim is that those collisions do not change the invariant measure. So the invariant measure now, if we have this container, the invariant measure will be truncated, because the objects are confined to some space. They will be confined, and now the measure becomes a finite measure. Because, well, I mean, you have to believe me, but you know, within that container, you have a finite measure.
But if you put balloon into this container, then vertical coordinate is not the same, because sometimes they hit balloon.
See, in this formulation, balloon is not any different than molecules. This is one of the objects. And part 2 says that the objects that have, you know, that are not point-like, they have to be disjoint, so whenever they meet. So for example, a molecule and a balloon collide. If you have 2 balloons, they would collide. But yeah?
And the eyes are the coordinates of particles.
Eyes? Well, this is just to count the number. Yeah, there are I molecules. In this formulation, it is I objects. Most of them are molecules. There is only one object one object is the ball.
Are you saying that the ball is one?
Yes. And all other objects are point-like. So, but you know, the formula is so general that I could make, you know, the objects any size, because it's a mathematical formula. Okay, so this is where probability comes from.
Molecule has a size.
Again?
Is the size of molecule positive or zero?
Okay, in our model, our molecules are point-like. The radius is 0.
But the balloon is not.
No, balloon is macroscopic. It's on the same order. Size comparable to the size of the container.
And how can it be in the same rise as a point molecule?
How can it be what?
Physically, how can a macroscopic balloon be in the same place in terms of formula with the molecules?
See, the formula is really about the motion of centers. Centers of objects that have mass. And part 2 says, well, and then we add radii to some of the objects, then we get collisions and the formula is good. Part 1 applies only to the motion of centers. Okay, the paper is extremely technical, and I will not even try to outline details. But I think that there's one formula, there's one idea that is really central to the proof, and it's not that hard to explain. So let's start with a data distribution. So if you're familiar with statistics, in Bayesian statistics, it's absolutely basic, because this is a distribution that describes your opinion about probability. This is a distribution on 0, 1, and somehow you try to describe your opinion about something, about probabilities, right? And well, the form of the distribution is that it is x to some power, 1 minus x to some power, right, on the interval 0, 1. And for us, what is relevant is how this density looks when the exponents are very large. And the case that we care about is when the exponents are very large but comparable. It turns out that if you want to know where is the center of this bump, the formula is very simple. You take the exponent, divide by the sum. In this case, it is 2/3. And then I'm not going to give you the formula for the variance or standard deviation, but the higher exponents, the thinner and thinner that the bump will be, so the probability will be more and more concentrated. Right? The distribution will be concentrated more and more about its mean. Okay, so I wonder, please have a look at this. This formula, that the right-hand side vector is the same as this vector. So what I'm saying is that velocities are actually irrelevant, to believe me, and we have to look on that positions. Now, what is this? So I didn't say that, but it's a natural thing it's a natural convention to put 0 level at the bottom of the container, at 0, which means that the coordinates of all objects have to be positive. Like, think about molecules, right? And now, suppose that we want to understand, we want to know how much probability is given to a certain potential energy. But what you have to do is you have to take the density and integrate it. And you integrate, so, like probability, you integrate density over that region where it is, where the formula applies, right? Outside there is 0, and so here what we have is, if we fix potential energy, because this is the potential energy, what you have here is a sum of non-negative numbers. And the sum is given because I say fixed potential energy, which means that you fix the value of this sum. And yi's are non-negative. Well, that's an equation for a simplex. And what you see over here is the volume of the simplex. So what it means is that if we integrate, we have something like, some variable to some power, some constant minus a variable to some other power. Okay, our paper is infinitely more complicated, but I'm trying to just give you an idea. And please note what is important. The exponents match, meaning that they go to infinity. When n goes to infinity, they go to infinity at the same rate. So first of all, they go to infinity, which means that we will have that effect of small standard deviation, and that the balloon will float closer and closer to a single point. And since the two exponents go to infinity at the same rate, it would be just one point and not different points. So that's the idea. Okay, you know what? Let me skip this.
So is this exclusively for the clone, or so D is 2?
Again?
Is your D equal to, so the clone match?
No. Our result is for any dimension. Well, one dimension is not interesting. 2 dimensions and higher. Okay, so since I don't have that much time, so let me skip a few slides, and we could always go back. And I want to show you these slides because they might be interesting. You see, I was talking about the invariant measure, but I guess I used to say the invariant measure, suggesting that there is one invariant measure. No. Here's a picture explaining that we have many invariant measures. Place all objects. So in this picture, that the molecules are not infinitely small. I mean, think about them as small spheres. Place them in such a way that all centers are on vertical lines and give them vertical initial velocities. They will just go up and down, up and down. And this will be completely different from the model that we discussed before. All velocities will be vertical forever. So, look, I mean, I cannot change that. I cannot prove that this is not true. There isn't one invariant measure. But what we can do is we can argue that under a small modification of the model, we have a single invariant measure. And I believe that this is quite natural because, claiming that molecules, reflect from walls randomly, that's, common sense suggests that that's probably the case. And, from the mathematical point of view, you could say that this is a cheap trick because it is very well known that in dynamical systems or PDEs, if you have some kind of model that is like a singularity is unpleasant, then you make it nicer by adding randomness. So in PDEs, for example, quite often you would add Laplacian. From my perspective, is you're adding noise, Brownian motion or white noise. And in this case, this is what we are doing. We are sort of smoothing things out, but by adding randomness. So really the question is, what is the right kind of randomness here? And I claim that the correct kind of randomness is what is known as Knudsen reflections or Knudsen model. I want 2 things. First of all, I want those reflections to be physically realistic, according to physicists. And second, I want them to preserve my invariant measure because our paper is based on that invariant measure. So my random reflections should not change the invariant measure. And these reflections are sort of, this is a kind of reflection that is memoryless, meaning that the blue line actually doesn't matter. It doesn't matter how the particle reached this point on the boundary. It will lead independently of the past in different directions. And, there's cosine alpha, so the highest density is, it will go up, and the lowest density is along the walls. Actually, Lambert was first by, 100 years or so, but he proposed this model of reflection for light, and Knudsen gets credit because he studied gas, rarefied gas. But actually the idea was known before Knudsen. Okay. So I want to show you Lambertian and non-Lambertian surfaces. So I'm trying to think if I could find the Lambertian, non-Lambertian surfaces here. Let's take this. Okay, do you see a green spot over there on the scene? Okay, so what it means is I shine on the glass, right? And there's basically a point over there, right? It's highly concentrated. So this is the specular reflection. The angle of incidence is the same as the angle of reflection. And the light just goes directly to the point. But I think you can see this point, right? Everybody can see this point. But what does it mean that everybody can see this point? It's random reflection. Because I shine at one point, but some rays go to every corner of this room. So this is the classical reflection, specular, and what you get is Lambertian at the scene. Now these are pictures illustrating Lambertian and non-Lambertian surfaces. But I can tell you right now, so I will explain that, but they are both fake, and I will just explain why they are both fake. So first of all, okay, so the moon has many, I don't know, some kind of geological, geographic features, and you know that probably the rocks have different color or something. But please note that if we go from the center along this ray, the brightness is constant. But if we go from the center of the orange to the boundary, the brightness or apparent brightness that we see is not constant. So Lambertian means that the apparent brightness, if you look at the surface at an angle, right, because the moon is spherical, right, we always see the same brightness. I mean, that's the apparent brightness. This is what you see. And it's not the case when the surface is non-Lambertian. Okay, now both pictures are fake. Why? Because if anybody asked me, I would say that the skin of an orange is actually Lambertian. And it's absolutely obvious that the photographer, I wasn't the photographer, but that the photographer chose light, some kind of lighting, to make the object look three-dimensional. So this is fake non-Lambertian. As for the moon, there's something I don't understand. You see, what I explained to you, the way I stated, this applies to surfaces that are uniformly lit by some source. And that I don't understand because, you see, when the light comes from the sun, right, different parts of the moon get different amounts of light because it depends on the angle, right? So the moon is Lambertian for no good reason. But that's the way it is. So what we proved with Jacek is that under this assumption, for reflections of molecules from the walls of the container, what we get is a unique invariant measure, and that's our justification for using this particular invariant measure. Okay, I will stop here. Well, thank you very much for your attention.
This is perhaps another physical question, but I'm still confused about this derivation of the barycentric formula. Somehow it is based on the assumption that the pressure, you derive it from fixed temperature. But if I think about what happens outside, so the pressure decreases, but the temperature also decreases significantly. Can you assume it to be constant when?
Okay, so first of all,
with
you know,
respect to Kelvin?
I have to blame somebody else. I didn't invent the barometric formula. Blame the physicists. You see, the thing is this. In our model, because of that formula for the microcanonical ensemble formula, there was this potential, energy part, and the velocity part. And the velocity, the energy was equidistributed, which means that the gas at the very top and at the very bottom has the same temperature, right? Because it's the energy per molecule. Now, concerning the real life, of course, we know that at the top of Mount Everest, right, the temperature is low, right? So I don't know. Who knows? I don't have an explanation. Maybe this has something to do with radiation. I mean, because the heat can escape into space, and it's somehow easier, in terms of electromagnetic waves. So maybe this is why up there the temperature is lower. But to be honest, I don't know. I'm not a physicist, and I don't have sufficient physical understanding of that.
Because there's less gas, so less diffusions.
No. It has to be some other effect, because if we are talking about just this model has this microcanonical ensemble formula, and according to this model, the temperature has to be the same everywhere. So there must be in reality, there must be some other phenomenon that makes the temperature lower up in the atmosphere, but not this.
Yeah, I similarly was trying to work out from early on about temperature and pressure was what was going on, because in the aim of trying to get the macroscopic result from the microscopic description seems interesting, and you can see that pressure, think about it there, that you can define pressure in terms of momentum transfers and molecules bouncing and stuff like that. But temperature I got hung up on, and the obvious thing to think about, say, is, that example where you had a column of molecules all on top of one another, and suppose they're elastic collisions, then that's reasonably easy to see what happens. What happens is that the molecules will bounce against each other, but it's as if they pass through each other. And the ones at the bottom will be exerting a pressure on the upward ones. They'll be holding the stack up. And so you can think of the pressure sensibly enough in that situation, but somehow the temperature is not so obvious enough to interpret temperature in terms of saying what's going on at the basic level of the objects.
Okay, so I guess should I say that I can say with pride that I was equally confused for about a year, because I was still a mathematician. And then I just accepted that temperature has to be everywhere, the same, and now I'm a physicist, and it's obvious. Well, let me tell you why it may not be that hard to accept equidistribution for a probabilist. In probability, we are familiar with Markov chains or Markov processes, and under some assumptions, the stationary distribution is uniform. And I sort of guess that in physics, these are some kind of similar assumptions about, I don't know, time reversibility or something. Therefore, this may be how physicists get that equidistribution. So that's one way to think about this. But as for temperature, I totally agree with you that at the very beginning, I thought that I must be wrong, and I finally believed in this when I talked to Martin Heyer, and he's not only a mathematician, he's a physicist, and it's obvious. So now I have an authority that I can support my claim with the authority.
And then another question was, the balloon, is it really a balloon, or is it a fixed size container?
Yeah.
I mean, that is, does the balloon expand or contract when?
That's right. So this is, these are the slides that I skipped. So our balloon is not a balloon. It's a solid object. Actually, it doesn't matter whether it's a shell or it's a solid object.
It doesn't
and it has to be spherical in our object, our past project, because we have a new project in which a balloon will be still solid, but we have different shapes, but that's like a project, in the future.
It doesn't change its size.
No. In our next project, we will put gas inside the balloon, because right now the balloon has no heat capacity. There's no heat, it has no, right? And heat energy inside, so we will put gas inside.
If the balloon in your model is ellipsoid, can you prove the same beautiful formula? Because you say that you
Not yet, but call me at the end of the month.
Okay.
No, okay, so we thought about this, but that would require some considerable amount of work, because make it spherical and simplify that.
I spoke to geophysicists, and they explained me that okay, temperature in mountains is much higher than here, and it was strange for me. But they think about temperature like speed of particle, and horizontal speed is very high because there is no pressure. I mean, there are no collisions. So I don't know what is temperature.
Well, that's a good point, because who knows, maybe what we feel as temperature,
Yeah, maybe if
like
there
the
are a
amount
lot
of
particles-
energy transferred to our body. And because there's low pressure, there's simply not enough energy transferred to our body. I don't know. I mean, this is speculation. I don't know.